Bismillah ar-Rahman ar-Rahim. Assalamu alaikum wa rahmatullahi wa barakatuh. And a very good morning. So alhamdulillah, today we'll be discussing, I would say, an interesting topic, almost 3 in 1, the kilogram, the Planck's constant, as well as digital twins. So I'll start by referring to this news recently released in 22nd September, where the Deputy Minister was highlighting the importance of verifying scales, measurement tools help to avoid accidents, prevent fraud. So Datuk Rasul Wahid, the Deputy Minister of Domestic Trade and Consumer Affairs, said the failure by traders, operators and construction developers to verify such equipment for trade activities constituted an offense punishable under the Weights and Measures Act 1972. So in today's world of advanced technology, all kinds of scams can happen. The same goes for fraud in weighing and measuring instruments. In construction work, for example, the failure of contractors or developers to get verified weighing equipment installed at concrete batching plants used to produce concrete grades in construction work can affect the stability of the structure. So what it's trying to say here is very important to comply to standards, and it can be disastrous if not compliant. So there are 2 acts that are relevant for measurements. Metrology is the discipline of measurements. So there's the first Act 675, National Measurement System Act 2007. This act plays a role as an umbrella act for all measurement legislation in Malaysia to enable individual organizations to have the means to make accurate and traceable measurements. Under this act, National Metrology Institute of Malaysia, Seri Merhat, has been appointed as the National Measurement Standards Laboratory to realize, maintain, or cause to be maintained the national measurement standards, which include certified reference materials for the purpose of providing national reference and traceability of units of measurements. The other one, Act 71, Weights and Measures, Act 1972. This act is to regulate weights and measures and instruments for weighing and measuring used for trade. The enforcement of this act is governed by the Ministry of Domestic Trade and Consumer Affairs via the Enforcement Division. In 2005, the Minister has granted a license to a company known as Metrology Corporation Malaysia to perform the functions of the Inspector of Weights and Measures, such as verification, stamping, except for enforcement duties. So this is an overview of the legal metrology structure in Malaysia. So we have the National Metrology Institute of Malaysia with the government concessionaire Metrology Corporation Malaysia, Seri Merhat. So overall, it will be under the Ministry of Domestic Trade Consumers. So in the case of manufacturers and suppliers who want to have something new, they will have to go to the NMIM. And for those who want to have their verification, validation, they will go instead to Metrology Corporation Malaysia, Seri Merhat. So they have their own respective roles, and things have to comply accordingly. What does the Quran say about measurements? So if we refer to Surah Al-Isra, the meaning of which, ayat 35, and give full measure when you measure and weigh with a balance that is straight. That is good, advantageous and better in the end. So this is just one of the verses of the Quran where Allah subhanahu wa ta'ala reminded us human beings to be very careful in terms of measurements. When we look at Surah Ash-Shu'ara, verses 177 until 182. أعوذ بالله من الشيطان الرجيم. إذ قال لكم شعيب ألا تتقون إني لكم رسول أمين فاتقوا الله وأطيعون وما أسألكم عليه من أجر إن أجري إلا على رب العالمين أوفوا الكيل ولا تكونوا من المخسرين وزينوا بالقسطاس المستقيم. Roughly it means when Shu'aib said unto them, so he was speaking to his nation, the people of Aikah, Ashabul Aikah, will ye not what evil? Lo, I am a faithful messenger unto you, so keep your duty to Allah and obey me. And I ask of you no wish for it, my wish is the concern only of the Lord of the worlds. Give full measure and be not of those who give less than the due, and weigh with the true balance. So this is another instance in the Quran where Allah subhanahu wa ta'ala reminded us to be careful, to be just when we deal with measurements. Of course, this is referring to Ashabul Aikah with Prophet Shu'aib, but the one that relates to us specifically also is there in Surah Al-Mutaffifin, verses 1 until 4. Bismillahir Rahmanir Rahim. Wailul lil mutaffifin alladhina وإذا اكتالوا على الناس يستوفون وإذا كالوهم أو وزانهم يخسرون ألا يظن أولئك أنهم مبعوثون. Roughly it means, in the name of Allah, most gracious, most merciful, woe unto the defrauders, those who when they take the measure from mankind demand it full. But if they measure unto them or weigh for them, they cause them loss. Do such men not consider they will be accountable in the hereafter? So, in this particular surah, verses 1 to 4, some commentators was regarding this as a Madani surah, but a majority attribute it to the period of the Meccan period. This misunderstanding has been caused by a tradition from Ibn Abbas, according to which when the Holy Prophet ﷺ arrived in Medina, the evil of giving short weight and measure was widespread among the people there. Then Allah sent down that particular surah, and the people began to give full weight and measure. As narrated by Nasa'i, Ibn Majah, Ibn Marduyah, Ibn Jarir, by Haki, Shu'aib al-Iman. But as we have explained in the introduction to Surah Ad-Dar, referring to Sayyid Abu al-Maududi, Tafhim al-Quran, the common practice with their companions and their successors was that when they found that a verse applied to a certain matter of life, they would say that it had been sent down concerning that matter. Therefore, what is proved by the tradition of Ibn Abbas is that when after his emigration to Medina, the Holy Prophet ﷺ saw that the evil was widespread among the people there. He recited this surah before them by Allah's command, and this helped them mend their ways. So this particular surah and the verses we have just described clearly show that measurements must be given accordingly in the right measure. So whether it's in terms of the weight or others, we Muslims are obliged to give full measure, inshallah. Now, the 2 points that I've shared just now shows that due measures is a big deal. So in the context of legislation in Malaysia, we have acts that we have referred to, and it has to be obeyed, and we need to be just. So the second case where I highlighted verses from the Quran Allah subhanahu wa ta'ala reminded us human beings, specifically Muslims, to obey His commandments in this respect with respect to measurements. So it's a serious matter. Now, let's get things clear first before we go into the details of the kilogram, followed by the Planck's constant as well as digital twins. When we go to see the doctor, for example, the nurse will ask us to take off our shoes and get our weight. So what is our weight? And the normal answer is in kilograms. So the weight is sometimes associated with kilogram. But then again, if we look at this first picture here, my weight on Earth is around 560 Newton. It is a force. So when you go to the moon, if you ever go to the moon, your weight has reduced from 560 Newton to 90 Newtons. So the interesting thing here we need to get clear is the weight is a measure of force. So if we look at this equation, a simple equation, weight, W, or if you write it in full, weight is mass times G. So G is gravitational acceleration. So if we look at the first picture, what it's saying is the weight, so the weight of this person is the mass of that person times a quantity called gravitational acceleration, which is about 9.81. Okay, 9.1 meter per second square. So roughly it's about 10. So if your mass, your actual mass is 56 kg on the surface of the Earth, your weight is 56 times 10 roughly. 9.81, we approximate it to about 10. So your weight on the surface of the Earth is 560 Newton. So you just multiply your mass, which is 56, times 10, which is the approximate value of your gravitational acceleration on the surface of the Earth. The case is different if you take the same person to be on the surface of the moon. The formula still holds. You have weight equals to mass times gravitational acceleration. But then again, for the moon, it is 1.6 instead of 9.81. Okay? So if you multiply 56 with 1.6, you get roughly 90 Newton. So that will be your weight on the surface of the moon. So the point that we want to drive here is your mass, whether you're on the surface of the Earth or on the surface of the moon, is constant unless you do not eat or you not drink for some time. Okay? So your mass may reduce by, let's say, from 56 to 54. But normally, your mass is constant. So what does this mean? Mass is therefore is a measure of the contents of the object. So in this case, the mass is defined as the content that made up this person, me, yourself. So our mass will not change whether we are in space, whether on the surface of the moon, or whether on the surface of the Earth. But it's actually our weight, which is under the influence of gravitational field or force, that will pull us toward the surface of the planet. So in this case, our weight here is larger than our weight on the moon because the gravitational pull on the Earth is bigger than the gravitational pull on the moon. So if you are in outer space and there's no surface nearby, or objects nearby, then you are weightless. Well, I don't recommend this for you, but if you go in the lift and the lift suddenly fell because of an accident, you will feel weightless. So you can also have weightlessness on Earth, but we don't hope for this kind of thing, which is, of course, in the sense of the accidents we want to avoid. Right, so the main thing here is the thing that we want to drive home is the mass. The mass is associated with the kilogram, kg, and it is a measure of the content of an object, whether it's human being, whether it's a ball or whatever. Now, not many of us realize that the kilogram, which is the SI unit of mass, it is the SI unit of mass. For example, if you're talking about time, you may talk about in terms of seconds, right? So in terms of mass, for the kilogram, we'll be focusing on kilogram. Now, not many of us realize that on the 20th May 2019, about a year ago, okay, the definition of the kilogram has changed after around 100 years. So imagine 100 years before, roughly, the original kilogram was actually put in it's actually inside a triple log vault somewhere in Paris, and it's actually under these two, veil glass container. So it's here. So this is the original kilogram that tells you this is 1 kilogram. And from time to time, every organization will send representative to Paris to ensure what they have in their respective countries is calibrated according to this artifact way back in Paris. So that was how we get our kilogram, which have to adhere, for example, our X that I referred to earlier in the talk. So when about a year ago, the world says goodbye to this artifact, the concept of kilogram, after around 100 years, on the occasion of the World Metrology Day. May 20th every year is the World Metrology Day. So scientists now want to make it easier so that every country now will be able to have the definition of kilogram in their respective countries. So they don't have to go to Paris to compare from time to time what is 1 kilogram and have to come back to their respective countries. Now, the thing that enables this remarkable thing to be realized is that they are resorting to a physical constant of nature called the Plancks Constant. And to realize this, they introduce what they call the Kibble balance. And this Kibble balance is sophisticated, yes, and so far only a few countries in the world have realized, have built, developed this Kibble balance, and accurately to several parts in 10 to the 8 accuracy, which is very, very accurate. So, but that doesn't mean that Malaysia or other developing countries will not be able to build Kibble balance. Of course, for lower budgets that are available, we may not have as accurate as those advanced countries, but the most important thing here is to understand first the concept, and then to try and build something that is near to the real accurate Kibble balance. Now, what you're about to see is a Lego Kibble balance, so which means made up of Lego, and it can actually give you about 1% uncertainty accuracy, which is quite good. And it's useful for promoting STEM, asking our students, our teachers, to understand STEM better. This is one of the things that might catch their attention apart from looking at the stars up there and objects in the sky. So let's have a look at this video, a short video, to highlight the Keeble balance made out of Legos.
Hi, we're scientists from the Measurement Standards Laboratory, New Zealand's National Metrology Institute.
In 2019, the International System of Units has undergone some major changes, and that includes the redefinition of kilogram, which is the unit of mass.
One way the kilogram can be realized is via a system called a Keeble balance.
Here, we have a Lego version of the Keeble balance. Although it is not as accurate as the actual Keeble balance, but it can show you how it works.
Keeble balances have two measurement modes, weighing and moving. In weighing mode, we place an unknown mass on one pan. We then provide a balancing force using electricity and magnets. How do we do that? We run an electrical current through the coil, and that becomes a magnet. This interacts with a permanent magnet, which is hiding underneath in here. The beam holding the two pans is free to pivot around a central point. A laser pointer and a light sensor track the beam so that we can tell when it's balanced. When the beam is balanced, the current in the coil is proportional to the mass on the pan.
In moving mode, we take the mass off the pan and we turn off the current. And then we move the coil back and forth through the magnetic field at a constant velocity. We drive this movement by using an electromagnetic force generated by a similar setup of a coil and magnet on the other side of the balance beam. This induces a voltage in the coil.
Comparing the electrical current from weighing mode with the induced voltage of moving mode leaves a simple equation that allows us to measure mass.
In a real Keeble balance, electrical measurements are linked to the Planck's constant, which is the fundamental constant in nature.
By making a connection between the kilogram and Planck's constant, stable, accurate mass measurements can be made anywhere in the world without relying on a physical artifact.
Here at the Measurement Standards Laboratory, we are building our own Keeble balance to realize the national primary kilogram for New Zealand.
All right. When we talk about this Keeble balance, we have already talked about the new SI definition of the kilogram, and it is now defined according to Planck's constant. The symbol here is H. So this is made possible without going into details of two quantum physics effects. The first one is called the Josephson effect, and the second one is called the quantum Hall effect. Now, without stressing about these effects, the bottom line is the energy is now for subatomic particles associated with the Planck constant through this HV equation. So this is the frequency of the energy that is being absorbed or being released. And this Planck constant being given the name after the person who introduced quantum physics. It was named after Max Planck. So the idea here is if you are having an electron somewhere in this energy level, and then this electron jumps down to a lower level. So from a higher energy level, EH to a EL lower. So once you do this, you are saying that you have discreteness of energy. So you don't allow for a spectrum of energy, continuum of energy, where this electron can jump anywhere from this energy level right down here. It can rest here, here. No, that's not allowed in quantum physics. So which means in quantum physics, the energy that's being allowed to do the transition is discrete. So that's why you have this equation. It is telling you every kind of energy that's released is in terms of integers. Okay, you can have 1 h nu, 2 h nu, and so on. So the concept here is to look at this Planck constant and tie it up to the concept or definition of the kilogram. Now, the first prototype Lego Keeble balance, as we've seen in the video, was done somewhere in the United States in NIST. So it is interesting to consider how an apparatus assembled from plastic bricks can measure the Planck constant, which is very, very small, in a classroom or living room setting with an uncertainty of only 1%. Now, we may not be looking at the comparable accurate Keeble balance in these national measurement laboratories, institutes in these advanced countries, but as I was saying earlier, to be able to construct and make an operational Keeble balance that can give you an accuracy of about 1% is cool. Now, the basic idea of this balance is, although the Keeble balance, if you look at the picture here, resembles what we call an equal arm balance, an equal arm balance is actually passive, relying on comparing an unknown mass to a calibrated one. So this was the 100-year-old definition that I was talking about. Previously, you will have something like the weighing. So you have to put the mass that you're comparing to with the one that you bring yourself. So this is the concept of the previous definition of the kilogram. They make use of the concept of equal arm balance. It is passive because you are comparing an unknown mass to a calibrated one, the one that we are saying that was kept in Paris. But on the other hand, for the Keeble balance, it is active. Okay? It is active. It's relying on compensating the unknown weight. So the unknown weight here, for example, you are comparing it with a known force. So instead of comparing with a calibrated mass, for example, the one that we had in Paris, now you are making use of force. Known force, in this case, the weight of an object is compensated by a precisely adjusted electromagnetic force. So let me go into detail. So the Keeble balance, it works in two modes. Okay? The first mode, this one here, is called the force or weighing mode, where the current is measured. So you put in your unknown mass there, so that this force, the weight, is balanced with the electromagnetic force. So your weight is made equal and balanced by the electromagnetic force, so that you'll be able to measure your current there, I. Okay? So there's no calibrated mass. In this case, it's just that you balance this unknown mass so that you balance it with the electromagnetic force. So the thing that we want to measure in this mode is the current I. On the other hand, once you are completed with this, I think part of this has been explained in this short video. Once you have completed and you registered the I here, you can now move to the second mode. It's quite independent. So in the second mode, the idea here, the velocity of the moving mode, so we are interested to measure voltage instead of current. So the idea here is you actually allow the coil to move here, to move vertically in the radial magnetic field, and a voltage is then measured. So you will have voltage V and then the current I from these two independent modes. So that's how the cable balance operate in two modes. Now, with the voltage and the current, essentially, what we are saying here is that you introduce the concept of power, electrical power. So in this slide, it is given the voltage is U, but if you look at the previous slide, the voltage was given the symbol V. So let's just call it V. So the electrical power is defined as V multiplied by current I. So this is the equation. So basically it's this one here. And without going into detail, you can represent this electrical power as R, H, frequency 1, frequency 2. So notice that this is your Planck's constant, H. So from this equation, we have introduced electrical power in terms of the Planck's constant. So what's missing now is to make the link between the mass with the Planck constant. So the first thing that we have obtained here is a relationship in terms of electrical power involving the Planck constant here. So the next thing we need to do is to look at the relationship between electrical power and mechanical power. So if you look at this, what it's saying is you are able to make a relationship between mg Vz equals to Vi. Okay? So the Vi is the same Vi here, which represents the electrical power. But what we want to say here is that the equation here, this equation, is called the Kibble equation. And the product here on the left of this equation is the mechanical power. And the one on the right is the electrical power. So again, the concept of power has been used here. And if you look at this statement, as it is the case with the voltage and current, the force mg and the velocity Vz are not measured simultaneously. So what it means here is, if you look at the left-hand side of the equation, you can see that you have mg, which is force, which is the weight, and you have the velocity. So this is how we relate it to the two modes of operation of the Kibble balance. So in mode number 1, just now we were talking about the weighing mode. We look at the force component. And the second mode, we look at the moving mode. We look at the velocity component. So the advantage of doing this is you do not need to measure weight or force and velocity simultaneously. And you are not actually compromising the accuracy of your mass in the end. So with this Kibble equation, the engineers and the scientists managed to see that you just need to separate the two mode operation, one in terms of the moving mode, the other one in terms of the weighing mode. So if I go back to this, so when you talk about the weighing mode, you put in your unknown mass onto the scale, and then you get your I. So you stop at that mode, you move to the next mode, which is the velocity mode. Okay, this is the velocity. Before you move from this mode to that mode, you remove the unknown mass, and then in this case, you determine your V. So by getting your V and your I, you'll be able to satisfy the right-hand side of both equations. Now, if that is done from the experiment, so we combine, because this is also P, so we combine this right side of this equation with the left side of the equation. So in the end, we'll be able to write as what we've seen on the slide. mgvz equals RH frequency 1, frequency 2, and you take this to the right side of the equation. So when you take that to the right side of the equation, then you get this final formula for mass. So if you get m in terms of Planck constant here, so these are all the things that will be associated with the Keeble balance. Okay, so the connection between mass and Planck constant has been shown. I've tried to make it as simple as possible, and that is the relationship between the mass and the Planck constant. So this is the real, if you look at the particular picture here, this one is one of the Keeble balances around the world, a very accurate Keeble balance. This one is in NIST in USA. Several other countries are also doing this, as we've heard, New Zealand, Turkey, Germany, and so on. Now, the last part of the talk, I've talked about the kilogram, I've talked about the Planck constant, and finally, to make the connection with digital twins. Now, the digital twins that I have to talk about is also related to the Keeble balance, so that we are aligned to the mainstream of the presentation, inshallah. Now, before we talk about digital twins and Keeble balance, let's look at the definition, one possible definition of a digital twin. There's one definition here, a physics-based dynamic computer representation of a physical object that exploit distributed information management and virtual to augmented reality technologies to monitor the object and to share and update discrete data dynamically between the virtual and real products. So this has been reported somewhere in 2018. Now, the main thing to take away from this definition is that you need three things to make up a digital twin. Okay? The first one, a model of the object. Now, this is, I think, simple to understand. When we talk about twins, identical biological twins, so you have two. So you're talking about twins. Triplets, you have three. So we are talking about identical biological twins, so you need two. So that's why when we talk about digital twins, you need to have two. One, the real object. The other one, which is modeling the real object. So that's number one. You need twins, a model of the object. But that's not enough. The next thing that you need is an evolving set of data relating to the object. Okay? You need to describe the dynamism of the object that you are representing. And finally, a means to dynamically update and adjust the model in accordance with the data. So you have an initial model relating to the object that you are looking at, and at the same time, this model will evolve because of the data that you collected. So we ensure that the model is able to be updated and adjusted accordingly to the data collected. So these are the three main aspects of the digital twin that we need to satisfy so that we are able to optimize the physical object that we're interested in. Now, having said that, we relate to the Keeble balance. The purpose of having digital twins is, for example, before we talk about a Keeble balance, a driverless vehicle, autonomous vehicle. There's no driver, so it has to be very safe. It has to be very safe. So in order to be safe, you need digital twins, so that whatever data that you collected, you feed it into the model, and the model will be updated, and then to give you a greater perspective, what's coming up, what's the predictive analysis, all those kind of things will ensure safety. Now, we apply it to the Keeble balance. The Keeble balance, if you look at it, there are many uncertainties, even though you're looking, for example, with the Lego Keeble balance. If you look at the actual Keeble balance, like the one in NIST USA, you will have the voltage and current measurement to deal with. You have the magnetic field strength. You have the coil alignment. You have alignment of optics, laser stability, external measurement of gravity, external vibration. So to be more specific, what it means is, by just looking at some of these uncertainties, for the balance, we are talking about stability of the voltmeter and resistor used to measure the voltage and current in the coil. Changes of the field strength of the magnet with temperature and time. Alignment of the electromagnetic coil with the field generated by the permanent magnet. Alignment and stability of optics used in the interferometer measuring position of the coil. Stability of the laser frequency used in the interferometer. Local acceleration due to gravity, the one I talked about, the G, so that it multiplies with your mass, and airborne and ground vibration. You see, the Keeble balance is actually on the surface of, for example, a table, and we have to account for airborne and ground vibration too. So there are almost 90 uncertainty components, even for the Keeble balance. So applying the concept of digital twins to the Keeble balance will ensure that our calibrated kilogram is very accurate. That is one of the critical things that we need to consider when we made it as SI unit for mass, for example. So I'm coming at the end. Concluding remarks. The first one, metrology, which is a discipline of measurement, is very much a part of Islamic science. Number two, quantum metrology is becoming more important. And finally, digital twins are important for high value and safety critical applications. Especially the last one here, if you're talking about data, we go back to this. The data, the model must be trusted. The data must be trusted. The updating of the model must be trusted. So if you have those satisfied, then you have a very reliable and optimized system to realize a system that is very useful for practical purposes. Okay, I'm open for Q&A if there's any. Thank you.
maximum or the minimum weight of the Formula 1 racer? Because bila kita tengok, they are very like slim, right? So what is your comment on that?
Slim? In what sense do you mean slim?
I was told that there is a maximum weight for the Formula 1 racer.
Okay. Right. There's one question here where what are the limits for the masses, the unknown mass, for the cable balance that you develop? Of course, there will be limitation. For example, the one that we've seen developed by the New Zealanders, the Lego version, if you put 1 ton of mass, it will break, definitely. So the thing here is meant to be looking at certain range of mass that the balance can give an accurate reading. So perhaps the one that we've seen just now, it may not go beyond 100 grams or something like that, I'm not sure. But for the one that we've seen in NIST, that one is definitely to calibrate the 1 kilogram. So it depends on what you want to measure. But the idea here is you need to have something that you can refer. So once you get something that you want to refer, just like 100 years ago, you have the unit of mass, which is 1 kilogram. So now you already measured 1 kilogram. So if you want to measure 1 ton or something bigger, you have already the unit. So you multiply. So that's the idea, the essence of getting this unit of mass. Okay, so thank you very much for listening to this presentation. I hope it is useful and eye-opener. I'm very excited if, for example, USIM will be able to realize this cable balance and explain them to various stakeholders, especially our students. Thank you very much. Wabillahi taufiq wal hidayah. Wassalamu alaikum warahmatullahi wabarakatuh.